All right, welcome to Tensor Lens. I have been living and breathing this topic for months, putting together a deep dive report on what is, without a doubt, one of the most exciting and ambitious technological races happening right now. Today, we're going to break it all down. We're talking about the quest to build a star on Earth, the incredible race for fusion energy.
You've probably heard the old joke in physics, right? That fusion energy is the future, and it always will be. For decades, it's just been this beautiful dream, always shimmering on the horizon, always, 30 or 50 years away. Well, something's changed. In just the last few years, people have stopped laughing. That joke isn't funny anymore. Because that mirage on the horizon, it's starting to look very, very real. So let's back up for a second. Why all the fuss? What is this 50-year promise? Well, it's the holy grail of energy. Think about it. Zero carbon, fuel that you can literally get from seawater, and no chance of a meltdown. I mean, it's perfect. But progress has been agonizingly slow. So what gives? Why now? Well, it's a perfect storm, really. Massive climate pressure, a fire hose of private cash, and, this is the big one, some game-changing technological breakthroughs. Just look at that number, over $6 billion. And that's just the private investment that's flooded into fusion startups since 2021. This isn't just a slow-moving government research project anymore. No way. This is fast money, venture capital chasing a $1 trillion prize. It has completely re-energized the field and kicked off this insane, high-stakes race to the grid. Okay, so how are they actually trying to build a star in a box? It's an unbelievably hard problem. I mean, you have to heat stuff to hundreds of millions of degrees and then somehow hold it all together. The global effort has basically split into three main strategies, three different bets on how to crack this thing. And to help us get our heads around this, I actually mapped out the entire global playbook on this whiteboard. It really helps visualize the landscape. You can think of it in three columns. Over on the left, you've got the establishment, the old guard. In the middle, you have the pure brute force approach. And on the right, you've got the clever hybrid newcomers. So let's break them down. First up, over on the left, we've got magnetic confinement. This is the OG, the establishment approach. The idea here is to build an invisible cage out of insanely powerful magnetic fields. You're basically creating a magnetic bottle to hold a superheated gas, called a plasma, in this donut shape. This is the path that's gotten the most love and funding for the last 50 years, and it's what the huge international ITER project is based on. And it's had successes. The jet Tokamaks in the UK set a record producing 59 megajoules. But it is also incredibly complex and mind-bogglingly expensive. All right, now for the middle column, inertial confinement. If the first approach was elegant containment, this one is pure, unadulterated brute force. Forget the magnetic bottle. Here, the idea is to take a tiny fuel pellet, way smaller than a peppercorn, and just blast it from all sides with the most powerful lasers on the planet. I'm talking 100 times the power of the entire US electrical grid, all focused on one tiny spot for a nanosecond. The goal is just to crush it so hard and so fast that it ignites into a tiny star. And spoiler alert, this is where the biggest news in 70 years of fusion research just came from. And that brings us to our third column on the right, Magneto-Inertial fusion. This is where a lot of the startup energy is. You can think of this as the hybrid approach. These companies like Helion and General Fusion basically looked at the other two and said, hey, what if we took the best parts of both? They use some magnetic fields to get things started, and then, bam, they use some form of rapid compression to trigger the fusion. They're aiming for the best of both worlds, hoping to build something smaller, cheaper, and faster. But I have to go back to that brute force laser approach for a second, because in December of 2022, at a place called the National Ignition Facility in California, scientists did something that's going straight into the history books. Just look at this chart. For the first time in human history, they achieved net energy gain from a controlled fusion reaction. They put 2.05 megajoules of energy in with the lasers, and they got 3.15 megajoules of fusion energy out. Now, it only lasted for a blink of an eye, but it didn't matter. It proved the physics. It proved that you can get more energy out than you put in. The dream was real. I love how Sir Stephen Cowley put it. He called it fusion's Wright Brothers Moment, and that's exactly what it is. Think about it. The first flight at Kitty Hawk didn't last long, but it proved that humans could fly. This experiment proved that controlled fusion ignition is possible. The fire's been lit. So that single moment, that one historic breakthrough, sets up this incredible drama that's playing out right now.
It's this epic two-track race to turn that scientific spark into an actual commercial power plant. And the race is between two very different competitors, big science versus fast money.
And what you've got here are two totally different philosophies. In one corner, you have big science, personified by the 20 billion plus euro ITER project. It's like building a cathedral. It's international, it's methodical, it's careful. But it's also slow. They won't even try full power fusion until the mid-2030s. And in the other corner, you have fast money. These startups are using that $6 billion in private cash to be nimble, to innovate, and to hit brutally aggressive timelines. They want power on the grid this decade.
And this is where it gets really mind-bending. Just look at these timelines. The startup Helion has already signed a power purchase agreement with Microsoft, promising to deliver fusion power in 2028. 2028. Other startups are right behind them, targeting the early 2030s. Now, compare that to ITER, which doesn't even plan to start its key power experiments until after 2035. The private sector is making an absolutely massive bet that they can get there a decade sooner. So the startups are going to win, right? Sounds easy. Well, not so fast. Because getting that one spark in a lab is one thing. Building a power plant that can do it millions of times a day, 24/7, reliably and affordably, that's a completely different universe of difficult. And this is where everybody, big science and fast money, is slamming headfirst into the same brutal reality, the engineering wall. Let's go back to our whiteboard. That Kitty Hawk moment was amazing. It proved the science works. Fantastic. But now you have to actually build the 747. You have to build the airport. You have to build the whole system. And that's where you run into these massive real-world engineering hurdles that stand between a cool physics experiment and a power plant that actually keeps your lights on.
So what are we talking about here? Well, for one, that net energy gain of 1.5, to be commercially viable, a real power plant needs a gain of at least 30, maybe more. Then there's a materials problem. The inside of a fusion reactor is one of the harshest environments in the universe. It gets blasted by neutrons that will make normal steel as brittle as glass. We literally have to invent new materials that can survive that for years. And get this, the best fusion fuel, tritium, is incredibly rare. So the power plant has to breed its own fuel inside the reactor while it's running. It's just an unbelievable list of challenges. And this really says it all. This is the moment we're in. For 70 years, fusion has been a physics problem. The main challenge was just figuring out how to make it work at all. Now it's an engineering problem. The question isn't if we can do it anymore. It's how we build a machine that can do it over and over and over, reliably and cheaply. So that brings us to the ultimate question. We've got billions of dollars pouring in, we've got ignition in the lab, and we have a very clear, if daunting, list of the engineering problems ahead. So, is this it? Is this finally going to be the decade of fusion? And who's going to get there first? Will it be the slow and steady tortoise, the big government-backed projects like ITER, designed to answer all the scientific questions for everyone? Or will it be one of the fast, agile hares, one of the private startups taking massive risks in the hopes of a massive payoff? But really, the biggest takeaway from all of this is that the stakes themselves have changed. This isn't just a race for a Nobel Prize anymore, or for scientific glory. This is a race to develop a clean, safe, and truly limitless source of energy that could power our world for thousands of years. It's a race for the future of the planet itself.